Alright, hello. So welcome to the June 2014 edition of Programmable Logic in Practice. And I'm going to be showing you how to do partial reconfiguration on a Spartan 6 device. So this is interesting because it's not officially supported partial reconfiguration, but it does work from Xilinx. So I'm going to load an example project here. And this will be probably one of the more complicated projects that we're going to be doing. So you can open the example project. So the example is made for a LX9 device. If you want to do it on something else, be aware you'll have to regenerate a FIFO and the DCM for whatever your device is. You know, if it's a different Spartan 6, for example, or whatnot. If you just change it here, I don't know if it pulls in all the changes you need. I think you might need to regenerate some of the cores. So let's take a look at the example. The example basically just has a input clock, 40 megahertz clock, and an output pin. It also has a TX and RX line, a serial connection, as well as two LEDs to show you some of the speed it's operating at. And we output a clock that's passed through a DCM block. So we have this DCM block here, and we're going to be reconfiguring it using partial reconfiguration. So to do the partial reconfiguration, this is where it gets a little more complicated. We're going to be using an internal interface called ICAP. I can show you that here. So it's in this block here is where it instantiates the ICAP module. So the ICAP is what's actually used to rewrite or reload the partial configuration data. So to do that, there's a FIFO, and the FIFO, basically data gets written into the FIFO, and then once the FIFO is full, you send a special command that dumps all the FIFO into the ICAP interface here. If you're using this yourself, be aware that the FIFO only has a certain size, which will limit you to how much partial reconfiguration data you'll be able to store. If you go over that, things will not work well. So this actually pulls in some register stuff from a different project I have, an open source project called the OpenADC project. So I've just sort of copied a bunch of stuff over, and I'll talk about that probably in another article. So there's an interface to the computer and whatnot. So to begin with, what we can do is just regenerate your standard run through to generate a programming file. So this will generate the base design, which we can program in. So I am going to use this is a Spartan 6 LX9 board. So this is the AVNet board, and it has a very convenient USB cable. We'll have to wait for that to finish. And I also have, let me just clear everything here. I also have an oscilloscope connected to, the design just outputs a clock line here, and I have an oscilloscope connected to that clock. And in particular, this oscilloscope is a picoscope model, and it can use it can switch the input to be either 50 ohm DC, so 50 ohm terminated, which is going to be useful to show you the differences in drive strength. Or we can just do unterminated, like that. So once that's done, let's program the FPGA with sort of the base file. Let's press to reload it. Yes, we want to. So this is what things look like to start with. So this is the output of the clock. Again, this is unterminated, so if I switch it to terminated, it actually looks quite a bit nicer, which is more or less what you'd expect. And it's 0 to, you see it's going to about 2 point something. It's actually supposed to be a 3.3 signal, but of course, because I haven't configured this to I haven't configured the output to expect any sort of proper termination, so that's why we get this. If I do unterminated, you see it goes a little bit below 0 and up to around 3.3. So let's see what we can do. So the first thing I'm going to show you is how to use the FPGA editor. So the FPGA editor lets you modify parts of the design. So if I open the FPGA editor and I just say post, place, and route here, it'll automatically load the design after place and route into the FPGA editor. Just give it a second here. Okay, so here's the FPGA editor. And all the windows are crazy, so you just hit this button right here and it really makes it look nicer, more or less. For some reason this window hasn't come back. Oops, there we go. So what this is showing you is more or less your entire design, and you can turn on and off things. But what's of interest is that it lets you edit parts of your design. So the first thing I'm going to do is save a new copy of this. And I'm just going to call this LX Reconfig diff. So this is an NCD file. So this is sort of a native file that has all of the information you really need. So let's go ahead and save that LX Reconfig. And exists because I've been playing with this already, and we do that just so we don't overwrite the original file, which is going to be very important. So what can we do in this? Well, one thing we can do is we can look at the output block. So if I sort these by type, I can find the IOBs, and I can find, let's just make these a little more obvious. If I go by name here, so I look for the IOB that deals with this pmod 1_p1, so that's the name of the output. So we could actually open that and we can view the settings. So if you opened your UCF file, you could see, for example, if you had configured anything like slew rates or drive strength. So we want to edit that, and to do that, before we can actually edit it, we have to, under the file main properties, a little window pops up here, and you have to change the edit mode to read write and hit OK. So let's change the drive strength to, for example, 24 milliamp, from 12. So to do that, I've opened the block. You have to hit this button here that says begin editing. And I'm going to change to 24 milliamp drive strength with fast slew rate. And when I hit save, this will automatically save the NCD file. Before I do that, I apply these changes and I look here if there was any errors or warnings. There weren't. And I save it. So we now have a new NCD file. If I had edited the original file, I could have actually just hit generate programming file, which would recreate the bit stream. This is handy. So say if you wanted to change some of the features, like the drive strength you were experimenting, you could just click through each of the drive strengths, hit generate bitstream, and reprogram and see what the results were. In this case, though, I've saved it as a different file, so I'm going to use the bitgen program to generate the bitstream file manually. So how do you do that? To start with, I start with a command window, and one thing you have to do is Xilinx has some special, so I'm using 14.4, some special tools that it will add to your path, and you just have to find, there's something called settings 64, I believe, settings 32 or settings 64.bat. If I run that file, it's now added them to the path. So for example, I can use this command called bitgen. Alright, so I go to where that NCD file was saved, so I just cd, and I just copy and paste from the Windows Explorer. Makes it easy, and let's make this a little wider here. In fact, let's make this even wider. so that this way you can hopefully see everything without dealing with line breaks. So you can use the bitgen utility to regenerate from an NCD file the bit stream. So there's a few options we can pass to it, and what do I want here? So if you look at the options, you can see, for example, this will be an option we'll use later, creating the partial bit file. For now, though, we can just use a very basic one. I'll add the W option, which overwrites, because I've been playing around with this a while. So bitgen overwrite. And remember that file, I saved reconfig diff.ncd, and I'll save it as, say, new bits dot bit. And it takes a second here, so it'll pop up any other. If you screwed up with something, it'll generate the appropriate warnings. All right. So, oops. If I go ahead and open Impact, I can use this, and let's make it so that you can watch what happens to the clock as I reprogram it. And this new bits file is the one I just created. So I hit program. And what you see is that, of course, the clock dies out when it's reprogramming. And when it's done, we can see that it's slightly more powerful than before. So let me save this waveform. Oops, come on. Seems like the Picoscope software is, there we go. So we have you can see this, the waveform is saved in the background there. Go ahead and make this a little easier to see. If I assign the original programming file, reprogram it, then you can see the waveform, the top's a little lower. So this is because the drive strength of the original one was 12 milliamps into the 50 ohm load, compared to it's now 24 milliamps in the background. The only problem is you can see how it's changing, like it drops out when I reconfigure, because I reconfigured the entire FPGA. So what I want to do now is actually generate just a difference file between those two, the original bit stream and that new file. So this requires a bit of a different command setup. So first I pass this option called active reconfigure, reconfig yes, so that says don't, basically it tells it that this will be a partial file and not to bring the FPGA down when I'm reconfiguring it. So I have to give it the reference bit stream, and this is a .bit file. It'll basically, everything's relative to the current bit stream programmed in, and it will give you a certain number of differences in frames. So that's the input bit file, and then I also pass it the NCD file. So that was the NCD file I edited. I tell it to overwrite with -w. Nope, -w is already there, sorry. And I give it the new name. I'm going to call it diffbits.bit. And I also add a flag called -b. This generates a special file called rbt, which is a raw bits. Basically, it's an ASCII version of diffbits. So we let that go. And what's really important to pay attention to, obviously if you get any errors, but because this is a partial file, it'll tell you how many frames of difference there were. So in this case, it says there's 1 frame different between this one and the NCD file. If I just make one change like that, I expect it to only be 1 frame indifferent. If you have a whole bunch of frames different, what's probably happened is you've generated a bit file from a different NCD file than the one you just modified, or you did multiple changes to the NCD file without realizing it. And you can see my article for more information about what sort of constitutes a frame and what that really means. And then Xilinx says the web talk is complete, so they send everything back to the motherland. Anyway, so if I program that bit file, so this is back to the original design. in theory, the impact tools are supposed to be able to work with a partial bit stream. So I can load this new bits file, and it'll actually realize that this is a partial file, and sometimes it'll tell you when you hover over it. In reality, though, it never seems to work properly for me. So if I program this, new bits. That's not the right one. I wanted diff bits. So let's program it to get it back to normal. So this is the baseline. And if I assign new configuration file, diff bits. No. So here's device file is a partial bit stream. So it picks this up, but when you program it, it just completely erases the FPGA. So it doesn't seem to actually properly deal with it. I don't know why. The Spartan 6 are not officially supported for the differential bit stream, so I think that might have something to do with it. I don't know. There's a lot of posts about it not working. But what we're going to do instead is use the internal core. So as part of the project, we had that ICAP core, and there's also a Python. So let me open this for you. A Python example, and this Python example loads the RBT file and downloads it to the FPGA. So this lets us sort of show you how you can do the partial reconfiguration using the FPGA's own internal interface. So this is closer to what you'd want to do in real life anyway. So to do this, I'm going to copy that RBT file. This is the one I just generated into the Python directory. If you want, so you can look at what this looks like. Let me just open it here. So the file itself just looks like this, and it's showing you 16 bits of data, and these are just commands that are going to be sent to the ICAP engine. The default ICAP can only deal with, I think, 2 frames in difference, because of the size of the FIFO. If you have more frames in different, you'll have to change that. Anyway, so I've copied the file here, and here's the Python code, so it just loads that diff bits. So if we run this, what we should actually see is that rather than the system going down, it's just going to dynamically reconfigure the one output, and there you can see it. So it's dynamically reconfigured the drive strength of the output, and we could actually switch between different drive strengths. So if I go back to this script file, I've already created ones for 2 milliamps, for example. So this diff bits was 24 milliamps. So if I load the 2 milliamps, see if it works. Yeah, so you can see there's the 2 milliamps. So this is showing you how to generate, use partial reconfigurations. Oops, I just changed the name on the other screen here. So I can dynamically switch the output power of the driver. So that's something you can't do dynamically any other way. You have to use the this sort of dynamic interface. And there is no 12 milliamp one actually. So the other thing I can do is I can actually modify the DCM block. So I already have one where I've done that, and I'll just show you if I run it. Oops. It didn't work because I think the file got deleted somewhere. What I'll do instead is I'll show you the whole process again. So what I'm going to do is find the DCM block, and it's the exact same process. So I open the DCM block, and you can see all of the parameters that were fixed at design time. So let's say, so we hit edit mode. Let us say we want to enable, what do we want to change? Maybe clock in divide by 2. So dynamically, this is something again that was fixed at design time. but we're going to change that. So if you do something wrong, it'll give you errors. Ooh, signals are not allowed. So something went wrong, and one rule I've already broken is I already made another edit in this file. So what I really should be doing is reloading the original NCD file and then resaving it. The reason being, otherwise I'm going to be modifying multiple things at once, which is fine if that's what you want to do. But I want to generate partial reconfiguration frames that just have one difference, and then I can actually apply multiple partial reconfiguration frames. So I'm going to save it, I'm going to replace it, and we make sure that we are in edit mode, which we are. And then I find that DCM block again. So open it up, switch on to edit mode here. And all I'm going to do is switch the clock in divide by 2. And you hit this button to apply it so you can check there's no warnings. And hit save. Okay, so everything looks good. Remember I overwrote the last NCD file, so I can just use the exact same command as before. And once again, I'm going to generate that diffbits file. Okay, and once again, all I do is I'll copy that RBT file back here. So I just named clock div 2, and that seems to be the same. So let's try this again. So there's the current output, and if I run it, what happens? Da-da-da! So you can see that it's actually applied it to the current design. And you can sort of get creative. A lot of this is unsupported, I have to warn you, so you have to be very careful how you do this. If I'm applying differences to different frames, in this case one of the frames is the DCM, a separate frame holds the information about the I/O blocks. I can, for example, switch, so I've already divided by 2. The base design would have this frequency doubled, and I can in fact, on this modified design, apply the 2 milliamp driver code. And you can see it's combining the clock div 2 and the 2 milliamp driver. Even though I don't have one frame with all of those in it, it's combined the two. Again, you have to be careful because when you overwrite a frame, everything in that frame gets overwritten. So you can only do that if the differences are held in different frames. And you can figure that out by editing the things in the FPGA editor, running the diff bits with bitgen, and seeing how many frames it generates. Does it generate one frame? If you modify both the things, you expect to see 2 frames generated. And that sort of tells you they are held in different frames. If you modify 2 things and just get 1 frame difference, obviously everything's held in 1 frame, so you can't do that. You have to do all the changes you want in that 1 frame. Hopefully that makes sense. So this is just a very, very brief overview of how you can use the partial reconfiguration with the Spartan 6, and this is reconfiguring the sort of using the internal interface. So it's quite powerful, especially when you consider you can use this, for example, to modify the phase shift of the DCM block well beyond what's provided through the simple programming interface, which is very, very basic. There's another example project where I use the combination of this programmable interface plus partial reconfiguration to give you sort of an infinitely variable DCM modification. So hopefully you found this useful, and thanks for watching.